Hello everyone, welcome to Learning Academy Foundation from Mr. Andrea. Have you ever wondered how a simple hello becomes a stream of zeros and ones? How a photo of your family, a song of worship, or a message of hope travels across the globe in milliseconds? Let's pause. Is it just magic, or is there a divine order hidden in the digital? Today, we are diving into the fundamentals of data representation, the sacred architecture beneath every digital experience. And we'll do it together, with questions that stir curiosity and answers that build clarity. What is a number base? A number base is a method for writing down numbers. For example, we normally use a number system called base 10, also sometimes called denary or decimal, which is all based on the number 10. Some people think that we developed a number system based on tens because we have 10 fingers. You might also know other number systems, for example, Roman numerals or tallies, as used in tally charts. We are only talking about how numbers are written down. This doesn't change the way numbers work. Let me ask you, why do computers speak in binary? You already know the computers only understand binary, which is a series of zeros and ones. But why? Could it be because simplicity breeds reliability? Let me know your answer writing down in the comments. So the number bases, units of information we're going to study are the binary, base 2. This is the language of machines. Okay. So they're in base 2. So 2 power 0 is 1, 2 power 1 is 2, 2 power 2 squared is 4, 2 cube is 8, 2 power 4 is 16, 2 power 5 is 32, 2 power 6 is 2 power 6 is 64, 2 power 7 is 128. And after binary, there is decimal, base 10, is our human counting system. The system we generally talk about numbers is in a 10-base system, also called decimal. In 10-base system, we talk about how many ones we have, how many tens, how many 100s, how many hundreds, etc. For example, the following number, 4567, is 4,567. Means 10, 7 ones, 6 tens, 500s, and 4,000s. And then after binary and decimal, we have hexadecimal in base 16. That's our bridge. Compact, readable, and efficient. Base 16 system uses digits from 0 to 9 and letters A, B, C, D, E, F. It groups of 4 bits represent each base 16 digit. And what is a bit? A bit is the basic unit of information in the field of computing and technology. It represents a binary digit, meaning a value that can be 0 or 1. Bits are the foundation of all digital information as they are used to store and transmit data. When multiple bits are grouped together, they form bytes, which are the most common unit of measurement in computing world. Bits are fundamental to the operation of electronic devices and the transmission of information across networks and computer systems. So just one choice, 0 or 1. But what about a byte? 8 bits, enough to encode a letter, a number, or a symbol, make 1 byte. How to convert between number bases? For example, if we have number 123, this is in decimal base. 123, since we want to transform in convert in binary, with this power 2, so we divide by 2. 123 divided by 2 is 61, with the remainder of 1. So we write 61 below number 123, and then 1 on the right. 61 divided by 2 is 30 with the remainder of 1. 30 divided by 2 is 15, remainder 0. 15 divided by 2 is 7, remainder 1. 7 divided by 2 is 3, remainder 1. And 1 is 1. So at the end, 123 in decimal base is converted to the binary 110111. Let's play game with numbers. If I give you the binary 10011011, how can converted to decimal base? Start from the rightmost that I put there in red. 1. 1 times 2 power 0 is 1. Then 1 times 2 power 1 is 2. Then there is 0. 0 times 2 squared is 0. On the left, going leftwards, there is 1. 1 times 2 cubed is 8. Then another 1. 1 times 2 power 4 equals 16. Then we have 0, the brown one. 0 times 2 power 5 is 0. The purple 0, 0 times 2 power 6 equals 0. And the leftmost one, 1 times 2 power 7 equals 128. And then we add 1 plus 2 plus 8 plus 16 plus 128 is 155. That is the result in decimal base. Now, if I give you the binary number 1010, can you feel its weight in decimal? Let me know your answer in the comment and I will give a heart to the one who scored correctly. So if I repeat the question, if I give you the binary number 1010, can you feel its weight in decimal? Let me know your answer. So if I say 2, okay, let's see this table. So we have decimal, hexadecimal, binary. 0, 0, 0, 0, 0, 0. 1, 1, 0, 0, 0, 1. 2, 2, 0, 0, 1, 0. 3, 3, 0, 0, 1, 1. 4, 4, 0, 1, 0, 0. 5, 5, 0, 1, 0, 1. 6, 6, 0, 1, 1, 0. 7, 7, 0, 1, 1, 1. 8, 8, 1, 0, 0, 0. 9, 9, 1, 0, 0, 1. 10 in hexadecimal is A. Starting with the letters 1, 0, 1, 0. 11 B 1, 0, 1, 1. 12 C 1, 1, 0, 0. 13 D 1, 1, 0, 1. 14 E 1, 1, 1, 0. 15 F 1, 1, 1, 1. So we have all the hexadecimal here from 0 to 9 and from A to F. Now I want to ask you another question. If I say 2A in hexadecimal, can you decode its decimal form? Pause and answer. Okay, the answer is 42. Congratulations to the one who answered correctly. Okay, let's see another example from binary to decimal. We have 101101. We always start from the rightmost, yes? So the rightmost is 1. 1 times 2 power 0 equal 1. 0 times 2 power 1 equal 1. 0. 1 times 2 squared equal 4. 1 times 2 cubed equal 8. 0 times 2 power 4 equal 0. 1 times 2 power 5 equal 32. And then we add these numbers. 1 plus 4 plus 8 plus 32 is 45. So 101 is in binary base. Into decimal base becomes 45. Okay. So now we are already good to convert between number bases. Binary to decimal by powers of 2. So for example, 101 binary is 1 times 2 squared plus 0 times 2 power 1 plus 1 times 2 power 0. That is 1 times 4 plus 0 times 2 plus 1 times 1. That is 4 times 4 plus 1, right? Equal 5. And then after binary to decimal, we are also good to convert from hexadecimal to decimal. This is by powers of 16, as we have seen before. And then, so binary to decimal, hexadecimal to decimal, and binary to hexadecimal. Binary to hexadecimal is by grouping bits in 4. So for example, we have 1110, 0111, 0001, 0000. Let's group this 4 by 4. Starting from the rightmost, 0000 in hexadecimal is 0, right? 0001 in hexadecimal is 1. 0111 in hexadecimal is 7. 1110 in hexadecimal is E. Because the first one is 2 power 3, 8, plus 2 squared, 4, plus 2 power 1 is 2. So 8 plus 4, 12, plus 2, 14. And the 14 in hexadecimal is E. Because after 9, there are other 5, 10, 11, 12, 13, 14. So the letter is E. Isn't it beautiful how structure leads to understanding? What about binary addition and shifts? Okay, so before continuing this lesson, I remind you to subscribe to my channel so you can see all the other contents and you let me smile, let's say like that. It's however free for you and very precious for me. Okay, let's say this question about addition. I want you to try to add these binary numbers. We have 1011 plus 100. I give you a multiple choice option. Let's say the first option is A, the second is B, the third is C, and the fourth is D. Okay, and then you can write your answer in the comments, and I will put a heart to the correct answer. So 1011 plus 100, how much would be? 1100 or 0111 or 1111 or 10011 10011. Option D. Okay. What about if we have 3 binary numbers? Let's say 1011 plus 1100 plus 0110. I repeat, 1011 plus 1100 plus 0110. What happens when the sum exceeds 8 bits? We have overflow. That's a reminder that even machines have limits. And what if we shift 101, that is represents number 5 in decimal, we shift left by 2 places, so we shift twice. We get 10100. That is 20 because it's 16 plus 4. The decimal is 20. So as you can see, it's a multiplication by 4. So shifting twice by 2 places is like we're multiplying by 4. Why? Because 2 times 2 power 2 is 4. So it's like we are multiplying by 4. Isn't that elegant? Let's talk about character encoding like ASCII or ASCII and Unicode. Do you already know my name, right? My name is Andrea. Yes. How does my name become, or your name, or whoever names become data? Through ASCII. Each character is a number. So let's see, for example, my name. A here capital letter A in binary is 10000001. And then lowercase letter n, 11011110. And then lowercase letter D, 11000100. And then lowercase letter R, 1110010. Lowercase letter E, 1100101. Lowercase letter A, 1100001. Wow, they become very big binary number, right? But my name is just with normal letters. What about if we use Mandarin or Hebrew letters? Or with Hebrew names. We don't have Hebrew letter or Hebrew names in the ASCII, right? So what we use? We use Unicode. Unicode is a global embrace of every language. Isn't that a reflection of God's love for diversity? Okay, now, the question is how to represent image. What is an image but a grid of pixels? Each pixel holds a color depth, that is the number of bits used to describe its shade. Number of gray shades or brightness level is determined by the bit depth, that is 2 power n, where n is the number of bits, called also brightness levels, available for each pixel. So 1 bit, 2 power 1 is 2 shades. 6 bit, 2 power 6 will be 64 shades. 8 bit, that is 2 power 8, will be 256 shades. 12 bit depth, 2 power 12, will produce an image consisting of each pixel within the matrix being able to produce 4096, that is 2 power 12, shades of gray or brightness levels. So as we can see, more bits means richer colors, but also larger files. And what about metadata? Metadata encompasses attributes about mobile activity and mobility data. It can be called duration, device location, data usage, favorite apps, and so on, but not the content. So the hidden story, like dimensions, resolution, even the camera used. Can you see how every image is both art and architecture? Okay, next, after image, I want to ask you how to represent sounds. How do we digitize a song? What we do is we sample it, taking snapshots of sound at regular intervals. The sample rate and sampling resolution determine quality. Isn't it poetic? Even silence as structure. Next is about data compression. Why data compression is essential for online video streaming? Data compression is essential for online video streaming, and it helps reduce the size of video files, making it easier to transfer data over the internet and allowing users to enjoy a smooth experience without interruptions or latency. Why store more when we can store smart? We have two types of compression, lossy and lossless. Lossy compression removes what you won't notice, like background noise. Often we can tolerate some loss of data through the compress-decompress cycle. Images, and especially video or audio, can be huge. HTTP bitrate is greater than 1 gigabyte per second. Big problem for storage and network. And then lossy compression and lossless compression preserves every detail. So the original GPG is 50%, lossless compression will be 33%, from a half to a third. And then there is Huffman coding. A tree of choices where frequent symbols get shorter codes. So let's try. If A appears 50 times and Z only once, which should get the shorter code? I repeat the question. If A appears 50 times and Z only once, which should get the shorter code? Let me know your answer in the comments. I'm curious to know if you get it. So it's efficiency, it's balancing efficiency and empathy in the workplace. Efficiency through empathy. Okay. Let's calculate if hello is stored in SHE 8 bits per character. How much will be? Hello is 5 letters. SHE is 8 bits. So 5 times 8 is 40. Correct. But with Huffman coding, I remind you that Huffman coding uses frequencies of symbols in a string to build a variable rate prefix code. Each symbol is mapped to a binary string. More frequent symbols have shorter codes. No code is prefix of another. So for example, A is 0, B 100, C 101, D 1. So hello, that which SHE stored in SHE will be 40 bits. With human coding, maybe it will be just 25 bits. Isn't that redemption? Less burden, same message. In all this, binary, pixels, sound waves, do you see the fingerprints of a creator? From chaos to code, from noise to meaning, God speaks order into every system. Just as he encoded love into our hearts, we encode meaning into machines. Starting from a source, then encoding, channel, and decoding. These three are make the noise. And finally, the receiver. The receiver will give feedback to the source. Let's remember, every byte we design, every image we compress can be a reflection of his beauty and purpose. Now that we have explored how data is represented, what happens next? Who manages this data? Who ensures it flows, stores, and executes? Next time, we'll meet the system software, the silent conductor of the digital symphony. If this stirred your curiosity, blessed your understanding, or sparked a new idea, like, comment, share, and subscribe to Learning Academy Foundation. Let's keep learning, creating, and serving together. See you the next time. Bye.